Hello guys, welcome to the channel. Today I have a really fun integral with some trig functions, so let's just dive straight into it. Cool, so here's a problem, and I'm just going to pause for a moment for anyone who wants to try the integral. Cool, so let's dive straight into it. So I think the first thing to see is that we have this square root, this radical here. But we have some squared functions, so it's really suggesting that there might be some way of rearranging and expanding and simplifying to try and cancel this square root out. So always whenever I have these trig functions, I always try and write them in terms of sine and cos. So since this is a secant and cosecant, I can write it like so. And then I can cross multiply to write this just as one fraction, just like so. So I've just multiplied this guy by sine squared x, and then cos squared x, and combine them together. And we have sine squared x plus cos squared x on the denominator, which is handy because we know that that equals 1 with this identity. So I can sub that in, 1. And now I can apply the square root to the denominator and the numerator. So 1 square rooted will just be 1, and then the denominator square rooted will just be cos x sine x. So I've just split the square root like so, and then you get cos x sine x. Whenever you square something and square root it, you just have to be careful that you've done it correctly, and because it's very important that this is always going to produce a positive value. So you need to make sure then that cos x sine x is a positive value. So I just quickly have here a graph. The red line is cos, the blue line sine. And here's our bounds to integrate. And we can clearly see that both the blue and red line is above 0. So when you multiply them, it's going to produce a positive result. Had our range be somewhere here, we might have had to chuck a minus in front of the cos x sine x. But in this case, it all works out. So now the next thing is to try and recognize that we can use double angle formulae, this one in particular. And if we rearrange it to make sine x cos x a subject, so it would just be half sine 2x. And I've just subbed that in just like so. And now it's just a matter of trying to simplify to produce, to make our lives easier. So just when you have 1 over a half, that's just the same as writing 2, multiplying by 2. And then I've just taken this 2 out, just like so, just so it's a bit cleaner. And then I'm going to write this sine 2x as cosecant 2x, just like that. And some of you may recognize from here that when you integrate cosecant 2x, you're just going to get the natural log of cosecant x minus cot x. But just in case you don't know it, we can go through it together. So there's a really nice trick for integrating cosecant, which is to multiply both by a fraction with both the denominator and numerator being cosecant minus cot, just like so. And remembering to use 2x instead of x, because we have 2x here. And then when you simplify that, you get this guy. And this is really promising. And the reason it's promising is because cot differentiates to produce cosecant squared. Oh, sorry, minus cot, to be more specific. Minus cot differentiates to produce positive cosecant squared x. And cosecant will differentiate to produce minus cosecant cot. So this signals that we can use this guy, which is saying that if we have the integral of a derivative on the numerator divided by this function, you should be able to multiply by some kind of constant and it will equal the natural log of that function. So we can clearly see from what we said that this denominator here is the function. So we can just say that, and we can chuck a box around it because that's quite handy. And actually now the easiest way to solve for k here is to work backwards. So it's to differentiate the natural log of fx to do that. And we can do that by setting y to equaling the natural log of cosecant 2x minus cot 2x. And then we use something called chain rule, which is just adding another variable in between to make our lives a bit easier. Whenever we have a new variable, we should chuck a box around it because it's quite important. So now if I write y in terms of u, it would just be like that. So what I've done is I've just subbed this guy out for u. And then here I can differentiate to get dy du, just like so. It's really pleasant. And I can also differentiate to get u du dx. So I have that box around there, and then du dx is this guy. That's really promising because it's looking like the derivative we have on the numerator. Cool. So now it's just all you can do is you can just multiply them, and that's because then the du's will cancel out, and you'll just be left with dy over dx. Um, and I'm just multiplying 1 over u, this guy, by this guy. That's what this is here. And now I'm just subbing out for u, I'm just subbing out cosecant 2x minus cot 2x, just so we have everything in terms of x, because that's what we wanted. And then you get dy over dx is this guy. And if we compare what we differentiated to our integral, we can actually see that it actually works perfectly, because we get 2 lots of what we're integrating, and we have a 2 on the outside, just like so. So uh, it's actually just works straight away. There's no constant, or I should say the constant's 1, so we know k equals 1. So now we can say that this guy differentiates to produce this, the natural log of cosecant 2x minus cot 2x. And not forgetting our bounds. Our bounds are very important. And now it's just a matter of subbing our bounds in, just like so. So I'm just remembering it's 2x, so it's going to be 2 pi over 3 and 2 pi, 2 pi over 3. And then here will be 2 pi over 6, which is just pi over 3. And then if we sub in the trig values and do some simplifying, just like so, then we will get our answer, which is the natural log of 3. So there you go. I really do hope you enjoyed the integral, and I look forward to seeing you guys next time.